Good afternoon, ladies and gentlemen. So today I want us to do how we can derive out the sum of a GP formula. So since we already derived out the sum of an AP formula if the nth term is known and if the nth term is unknown. So I want us to derive out the sum of a GP formula. So we all know that for a GP we have the first term which is A plus. So the second term is R times the first term. So the first term is A times the R times the first term. So this R represents the common ratio. So between the second term and the first term, the difference is the common ratio, which is the R. Then for the third term, so since between the first and the second, the difference is R times. So between the difference between this one and this one is R. So this one I'm multiplying by R. So for the third term, I'm going to multiply this one by R. So it should be A R squared plus. So it still goes on and on and on. Then you go to the for the last for the last second term it will be A R to the power n minus 2. The reason you're subtracting with 2 is because it is the second from last. Then plus the last term will be A R to the power n minus 1. So this is the how we add terms for when it comes for a GP. Then using this formula now, we are going to multiply by the common ratio throughout. So we're going to multiply by the common ratio in this same formula. So we have even Sn you're going to multiply by R, so it will be R Sn is equal to, so A times R we are going to have A R plus this A R times R we are going to have A R squared plus this one will be A R cubic plus, so this continues. So this one A R to the power n minus 1, if we multiply by R we are going to have A R to the power n minus 1, because 1 R we are going to subtract with 1 R. So this out of these two we are going to subtract 1, which means we are going to remain with n minus 1. Then plus, if we multiply by this one by R, this one is going, we are going to eliminate this one, so we are going to remain with A R to the power n. So for the second from last, if we multiply this one by R, we're going to eliminate a 1 from here. Out of n minus 2, we're going to eliminate, we subtract with 1, because R is to the power 1 when we multiply. So we're going to have n minus 1, which is here. Then for AR to the power n minus 1, if we multiply by R, since R is to the power 1, 1 minus 1 gives us a 0. So we're going to remain with AR to the power n. Now, for this one, when it comes to sum of an AP, we were adding, but for this one, we'll be doing what we're going to subtract. So this one will be Sn minus. So we're going to subtract this and this. So it will be Sn minus R Sn is equal to. So if we subtract throughout by this one, so we have AR. So we have AR. So these two they will cancel. We are going, this means there is 0. This means there is 0. Even this one, it means we have another one which is 0, which is R squared. So it means we have R cubic. So this one will go. This one will be eliminated because we have something similar which is before this term here. Plus this one and this one, they will also be eliminated. So we are going to, what are we going to remain with? So here we have A here, because here we don't have A. So we are going to have A minus, here what are we going to, are we remaining with? We are remaining with AR to the power n, because here on top we don't have AR to the power n. So we are going to remain with AR to the power n. So when you go back this side, we have Sn and Sn. So Sn is common both sides. So we're going to eliminate Sn. So we're going to factor it out Sn. Then here we're going to remain with what? With the 1 minus. If we eliminate Sn here, or we subtract it out, we're going to remain with the R is equal to. So here, even here, as you can see, there is one which is a is common on both sides. So we're going to, if we factor out a, we're going to remain a. Then here we're going to remain with 1 minus. If we factor out a, here we're going to remain with a to the power n. Then here we can divide throughout by 1 minus r. Even here 1 minus r. So s of n is equal to a 1 minus r to the power n over 1 minus r. So this is the formula for sum of a GP. So this formula only applies if r is less than 1. So if r is less than 1, this is the formula we have to use. So this is the sum of a GP. So yes, what if r is greater than 1? So if r is greater than 1, we're going to have Sn is equal to a r to the power n minus 1 over r minus 1. So this is if r is greater than 1. So you have to be mindful of these two formulas. You have to know the difference when you have to use this one and when you have to use this one. So this one is only used if r is less than 1. Then for this one, if r is greater than 1. Then now let's move to sum to infinity. How we can derive out the sum to infinity. So for sum to infinity, so we know that for a sum of a GP, the formula is given by if Sn is equal to a 1 minus r to the power n over 1 minus r. So for this formula, for sum to infinity, it only applies if r is less than 1. So that's why we have gotten this formula, because r should be less than 1 when it comes to sum of to infinity. So for sum to infinity, since r is what? R is less than 1. Then it means r to the power n will be doing what? R to the power n, as it is, it will be approaching 0. Because if it's provided it is less than 1, it means it will be approaching 0. So Rn will be approaching 0. So the value of r to the power n will be reducing. So to be going closer and closer and closer towards to 0. So r to the power n will be approaching 0. So you're going to say s of n is equal to, as r to the power n approaches what? Approaches 0. So we now go to limit. So at this point we are on limit. So a, then 1 minus r to the power n over 1 minus r. So this 1 minus r will be doing what? Will be approaching 0. So as this one will be approaching 0, we're going to remain with a, then 1 minus, so this one will be a 0 over 1 minus r. So 1 minus 0, this gives us a 1. So a times 1, so sum to infinity is equal to, so here we are going to remain 1 minus 0 gives us a what? A 1. So a times 1, which means we have a over 1 minus r. So this, therefore this is the sum to infinity of a GP. So this is how this formula came about, because r to the power n, since r to the power n is less than 1, so since it's less than 1, it will be approaching closer and closer towards to 0. So we're going to say r to the power n as it is approaching 0. So where there is r to the power n, you're going to replace it with a 0. So when you replace it with a 0, it will be 1 minus 0, which gives us a 1. So a times 1 will give us a. Then this part you are not replacing r to the this r, because this one is to the power n. So we only replace if r to the power n replaces 0. So this one doesn't have to the power n. So this one, the down part we're going to maintain the denominator, but for the numerator, that's where we're going to replace, because the numerator is r to the power n. So therefore this is the formula for sum to infinity. So this formula only applies if r is less than 1. So the reason why we're saying r to the power n approaches 0, we're not saying r. The reason we're saying r to the power n as it approaches 0 is because when suppose r to the power n if r is less to the power n, it will approach 0. This expression will approach 0 faster than this expression when when it is 1 minus r. Because okay, let's take for instance to say that we have r is 0.3, then you have n to be to the power 2. Yeah, so 0.3 squared. So 1 minus 0.3 squared. So 0.3 squared gives us 0.9. So when you say 1 minus 0.9, you're going to have 0.1. So 0.1 is very close to 0. So it has approached 0 far earlier than this one. And then since we know that r is 0.1, it's 0.3. So 1 minus 0.3 will give us 0.7. So it means this expression which is on top here has approached 0, or as approached nearby 0 more than this expression, because this one is far from 0 because it is 0.7. But for this one, when you punch it out, 1 minus 0.3 squared. So 0.3 squared gave us what? 0.9. So 1 minus 0.9 gives us 0.1. So 0.1 is very closer to 0 than 0.7. So that's why when you say that r to the power n approaches 0.